Hi everyone! In this video we look a little closer at the stereoselectivity of the E2 reaction. In another video we showed how a strong base, like an alkoxide or hydroxide, can react with an alkyl halide or tosylate to produce an alkene product. In this reaction, the strong base deprotonates a beta hydrogen, while at the same time the leaving group leaves. This is a stereoselective reaction for the E-alkene, but sometimes the Z-alkene can be produced exclusively. Here, we will explore how to predict the stereochemistry of the product in these reactions. To understand the stereoselectivity of this reaction, we must look at the orbitals. The CH bonding electrons are ultimately going to be what forms the pi bond in our alkene product. And in order to form that pi bond, these electrons have to have somewhere to go, and that is into the sigma antibonding orbital of the carbon leaving group bond next door. In order for these orbitals to overlap, the carbon-hydrogen and carbon leaving group bonds must be anti-periplanar. Anti meaning that they are on opposite faces of the molecule, and periplanar meaning that they are in approximately the same plane. So as the base deprotonates the beta hydrogen, these bonding electrons form that pi bond, and as that antibonding orbital is filled, the carbon leaving group bond breaks and that leaving group leaves. This generates an alkene with very specific stereochemistry. We can see from this diagram that R1 and R3 are on the same side, and they will be on the same side of my alkene product. R2 and R4 are on the same side and will remain on the same side in our alkene product. We can predict this stereochemistry by using Newman projections. So let's practice doing that for a few examples now. Let's use R2-bromobutane as an example here to see how we can predict the stereochemistry of our alkene product. In this example, we know that we're going to be eliminating one of these two beta hydrogens, and that is due to the fact that we know that these reactions are regioselective and will form the more substituted alkene, unless of course we're using a sterically hindered base. The best way to see this anti-relationship between our leaving group and a beta hydrogen is to use a Newman projection. So we can fill out this Newman diagram. We have the bromine. If we look down the bond this way, that's your little I, we would see bromine, hydrogen, and methyl. And in the back, we would have methyl and our two hydrogens. Which group in this Newman projection is anti to my leaving group? Our leaving group is the bromine, and 180 degrees, or anti to that bromine, is the hydrogen, and that is one of our beta hydrogens, specifically this beta hydrogen. If this molecule undergoes an E2 elimination, which it can in this relationship, we would get an E-alkene. These two methyl groups are on opposite faces and will remain on opposite faces in our alkene product. In this example, there is a second beta hydrogen that could also be eliminated in this reaction. So if we rotate about the single bond in our Newman projection 120 degrees, let's hold the front steady. So we'll keep the bromine and the hydrogen and my methyl group as such in the front, and in the back we'll rotate those groups clockwise 120 degrees. So now I have still an anti-periplanar relationship between my leaving group and a beta hydrogen, but now you can see that the methyl groups are on the same side, they're gauche to one another, and this conformation leads to a Z-alkene compared to the E-alkene. So when there are two beta hydrogens, both the E and the Z-alkene are possible. However, because of the lower energy conformation here and the stability of the E-alkene, the E-isomer is the major product. Now let's look at a couple examples where there is just one beta hydrogen. In our first example here, we know that the leaving group and beta hydrogen must be anti-periplanar. I'm just going to draw in that beta hydrogen here and circle it for us so that we know what we're looking at. Here in the Newman projection, if we look down this bond, we would see our bromine here and our hydrogen here, and the benzene ring, I'll abbreviate it as PH for phenyl. Phenyl as a substituent is what we note the benzene ring as. In the back, we have the methyl group, our beta hydrogen, and then the ethyl group, CH2CH3. In this conformation, are my leaving group and my beta hydrogen anti-periplanar? Yes, they are. We have my leaving group here, and it is 180 degrees anti to my leaving group. So the elimination can occur through this conformation. So in the presence of methoxide ion, the beta hydrogen can be deprotonated and our leaving group can leave, and we will form an alkene product. And this alkene product will have the methyl group and the phenyl group on the same side, and the hydrogen and my ethyl group on the same side. So that would look like this. My phenyl group and my methyl group on the same side of my alkene, and on the other side we have the hydrogen and the ethyl group, CH2CH3. And if we rank these groups according to the Kohn-Ingold-Prelog rules, we would find that the stereochemistry of this alkene is E. Because there is just one beta hydrogen, only one stereoisomer is possible from this reaction. If we look at the second example, again, building our Newman projection by looking down that bond in the same way, the front looks the same. This is my phenyl group. And in the back, the methyl group is now here, my CH2, CH3 group, and my beta hydrogen. Are the leaving group and beta hydrogen anti in this conformation? They are not. They are gauche, and so this conformer is not the reactive conformer. We must rotate about that bond to give a conformer where the beta hydrogen and the leaving group are anti. So what I need to do is rotate the back around 120 degrees such that these groups will be anti. And I have the leaving group and beta hydrogen anti now. So this is the reactive conformation. After elimination, we'll find that the phenyl group and the ethyl group will be on the same side of my alkene, and the hydrogen and the methyl group will be on the same side of my alkene. If we use the Kohn-Ingold-Prelog rules to rank substituent groups on each carbon of this alkene, we would find that this is the Z isomer. Again, just one beta hydrogen here means that there's just one stereoisomer possible in an E2 elimination. Before we move on from this example, I want to ask you a few more questions. What is the relationship between our reactants in this set of reactions? These reactants are diastereomers of one another. They both have two chiral centers, but differ in the configuration of just one of the two chiral centers. We have the SR and the SS stereoisomers here. Now consider the stereochemistry of my products. How are these products related? Our products do have the same connectivity, so they're not constitutional isomers. They are not superimposable, so they're not identical, and they are not mirror images, so they're not enantiomers. That means that they are diastereomers. The importance of looking at the stereochemistry of my reactants and the stereochemistry of my products allows us to see that this reaction is stereospecific. where stereoisomeric reactants give stereoisomeric products. Now we understand why the E2 reaction is stereoselective thanks to a little help from molecular orbital theory. Moreover, we can use Newman projections to visualize that anti-relationship between our leaving group and the beta hydrogen to predict the specific stereoisomer that is produced in these reactions, whether it be E or Z. Thanks for watching.